about the electrochemical driving force. Last time we introduced the concept of the chemical driving force, which was based mainly on the concentration gradient. And we also looked at the electrical driving force, which is based on the charge of the particle in question and the state of the cell. So the polarity of the cell, right? The difference between negative charge on the inside of the cell and positive charge on the outside. So today we're going to put both of those forces together, and we're going to determine the overall direction of the electrochemical driving force. And bear in mind, this is specifically for instances where we have forces acting in different directions, okay? We talked about a really simple example. If both forces were acting in the same direction, we would simply sum those forces together, and that would be the net direction. And then the overall magnitude would be the size of the driving force. But things get a little bit more tricky when we have electrical and chemical forces that are acting in opposite directions. And so we're going to talk about how we can determine the actual direction of movement. Okay. Okay, so we're determining the direction of the ECDF, and that is the electrochemical driving force. Okay. And so first of all, we want to identify what direction are our forces acting on individually. Okay, so identify the direction of the chemical driving force independent, and then of the electrical driving force independently as well. And we can have several different scenarios here. So let's look at what those are. So we can have the ECDF, or the EDF rather, and the CDF. So the electrical driving force and the chemical driving force are acting in the same direction. And that we said was really straightforward, right? That would result in an ECDF that moves in that direction. Now we can have a scenario where the EDF and the CDF, our two forces, are in opposite directions. And that we'll see is the case for potassium when we look more closely at the cell. Okay? And so what we're going to do here when this happens is we will compare the equilibrium potential for the ion in question. We talked about what the equilibrium potential is, the force that brings the net movement to zero, okay? And we're going to compare that with the membrane potential. And we also talked about what the membrane potential is. It is the force acting on the membrane brought about by the separation of charge, okay? That unequal distribution of charge across the membrane. And so when we compare these two variables, we know that the equilibrium potential is indicative of which of our two forces? Which of our two forces is the equilibrium potential indicative of? Was it the chemical or the electrical? The chemical driving force, yeah, the concentration gradient. So if that is greater, then the net movement is going to be in the direction of our chemical driving force. If the membrane potential is greater in terms of the value, then the net movement will favor the movement of the electrical driving force, okay? And so by that principle, we can have 3 scenarios here as well. So our first scenario, if the equilibrium potential of the ion in question is greater than the membrane potential, then chemical driving force is greater than the electrical driving force, and the ECDF will follow the chemical driving force. Okay. So first scenario. The second scenario is if they're equal, right? So if the chemical driving force is equal to and opposite of the electrical driving force, what do we expect to see here? So if the chemical driving force is equal to, and we know that it's opposite, the electrical driving force, what do we expect to see? What kind of electrochemical driving force? We talked about this, yes. Resting, right? So there's no net movement, right? We talked about that. The particles would be at equilibrium. So if the chemical driving force is equal to and opposite, right? This is the opposite end of the spectrum, then the ECDF, which is our combined forces, equals 0, and there is no net movement. Okay, this is where we have equilibrium. And then our third scenario is going to be opposite that first scenario, and that is if the membrane potential is greater than the equilibrium potential. So this should have been if the equilibrium potential is equal to the membrane potential. Okay? So if the membrane potential is greater than the equilibrium potential, then we see that the EDF is greater than the CDF. So our electrical driving force is greater than our chemical driving force. And what do you think will happen here? Which of the forces is stronger? What's the net movement? The electrical, exactly. So the electrochemical driving force will follow the electrical driving force. Okay? So basically, in order to see what direction our net movement takes place in, we must look at the equilibrium potential value and the membrane potential value. We'll compare them if the forces are in opposite direction, and that will tell us what net direction our particles are moving in, and then we can just subtract those values, right? The larger value, we subtract out the smaller value, and that's going to give us our net magnitude, so the strength or the size of the driving force. All right, any questions? Any questions on that yet? Okay, so let's keep moving here. Okay, so this illustration here summarizes that concept of determining the direction of the electrochemical driving force. So on the left, this is if the membrane potential is weaker than the equilibrium potential. And this is looking specifically at the ion potassium. So potassium is a positively charged ion, right? And so it has a higher concentration inside the cell and a lower concentration outside the cell. And that gives it a concentration gradient of higher in the cell, low outside, so a chemical driving force moving out of the cell. Alternatively, potassium is positively charged, and so it's going to want to get inside the cell where this negative environment exists, right? If we have a membrane potential of negative 70 millivolts, this means that the inside of the cell is negative 70 with respect to the outside of the cell, so it's more negative. And so we talked about the polarity, and we talked about the electrical driving force wanting positively charged ions to get to the negatively charged environment inside the cell. So as you can see, we have two forces that are moving in different directions, and when we combine these forces, we're going to subtract the smaller force from the larger force, but we'll look at these two values to determine the net direction of the ECDF. So as we can see here, the equilibrium potential is a larger value, it's negative 94 millivolts. And so which of our forces is the net direction going to follow? If the equilibrium potential is greater than the membrane potential, which of our forces will the net movement favor? The chemical driving force. Excellent. So we know in this scenario, net movement is going to be outside of the cell, and we simply subtract the strength of our forces to determine the strength of that net movement. Okay? On the right, it's an opposite scenario. So if the membrane potential is stronger than the equilibrium potential, you can see that down here by the value. So the membrane potential here is negative 100. And our equilibrium potential for potassium, which is the same, right? This is going to be the same for specific ions, is negative 94 millivolts. And so we have a equilibrium potential that is weaker than our membrane potential. So the net direction of the ECDF will favor the electrical driving force, which will be into the cell. And again, we simply subtract out the smaller electrical driving force, the smaller chemical driving force from the larger electrical driving force to determine the magnitude of that force.